you can give me a well done homework 5, that'll be awesome. Or homework 4, I'm sorry. That'll be awesome, right? There's no rush. If you give me the partially done homework, what is the point for me? I don't want to punish my students. My goal is that I want my students to learn these useful skills. Do you agree? Tomorrow noon, right? If you give me a better one, well done one, it'll be awesome.
Do you know we might be having that issue with like one of the specifically? I'm having the same issue as him where the one tool just still won't finish running. I got everything else to run, but
I do not know. But this office hour 4 to 5, I will be here. Okay. If nobody is online for the office hour, you can just I can just go to the computer lab to help. Okay. If there are many other students online, and we can just answer some questions in office hour. Then after 5 o'clock, I can go with you.
Would you prefer I come in person then, or just call what you want to in person?
Office hour is held.
Office hours are held virtually.
But after 5 o'clock, I can go to you go to the computer lab. Right. So today I'm going to give you 3 examples, and if you have the calculator and the piece of paper, please bring them out. Okay. So these 3 examples are very, very important. As I said, I'm a machining guy, right? So whenever we have some new materials, new tools, and we can use our hands to do some hand calculations and to estimate the cutting force, the energy consumption, and also the tool life. And even though it is not very accurate, but still we can get some sketchy idea. So these are 3 examples. And the first example is about this is a cutting force. Before I give you the example, I still want to refresh your memory using these 2 diagrams. For this orthogonal cutting, we have this velocity, the cutting speed in the cutting direction, the tool, the tip. So we have this is F. So this is R. R is the resultant force. Resultant force can be decomposed into the F. So this is capital F is along the rigid face. This is the friction. That is because of friction. So this N is another one which is perpendicular to R. This N is along this shear angle. Shear plane, we call shear plane. So F is along the rigid face, N is a shear plane. So this angle is called beta. And we are going to, based on this diagram, we are going to also, so this R can also be decomposed also not orthogonally in another way. This is FC, the cutting force, FT, the thrust force. So how can we use this diagram to solve the problem? And also the specific energy, force and energy, and they are related, right? So the power actually is energy per unit time. Do you agree? But we just care about the energy per unit time, so we call power. For our case, FC is the cutting force. Cutting force multiplied by the speed equals the power. Do you agree? So someone say, oh, there is a time t. Okay, if you count time t, F, this is V, right? And this is time t, V time t equals V multiplied t equals what? Equals the distance, right? Distance the tool is going. The force multiplied by the distance in the force direction is what? Is work, right? The work. Okay. So because the energy is conserved, the work you have done equals the power you just consume. The power multiplied by T is the power multiplied by T is the total energy, right? So this one, because we just, as I said, we just care about energy consumption per unit of time. So we don't have T here. You understand? Okay, so the specific energy, and whenever we see specific, that means how much energy we need to apply, we need to consume if we want to do the specific volume. So the total energy per unit volume of material removal, UT. And UT is defined as how much material the power, right? The total power energy, FCV is my power, total energy. How much material I just remove. How can I calculate it? So W is the width of the workpiece, width. The T0 is a uncolored chip signal, right? Width, uncolored chip signal is a cross-section area. Then multiply the V. Suppose I have T here. The time T, Vt is the distance in this direction, right? So this is my volume if I have T here, right guys? But here, if I multiply T here, this one is the total energy, but this guy contains the T, and this guy contains the T also, T, just cancel out the time. So that's the reason the UT can be written in this way. Do you agree? Okay, so can be simplified FC omega T0. V, this is V here, right? V and cancels this V. Any questions? No question. So this is total energy. The friction energy as specific energy, and still this is the total volume, right? You agree? Total material removal, the volume you just remove material. Omega T0V, the total energy in friction, because of friction, it equals the friction F in the workpiece multiplied by this guy's CC, the chip velocity. That makes sense? Okay, so now this one is a VC and V. VC and V, how can we calculate the VC and V? Because the chip, right? The T0 multiplied by the V equals VC multiplied by the T. So this is my material I just removed. So T0 is an unconductive signals, right? T0 multiplied by my V, the cutting speed, equals my T multiplied by my VC. Why? Because the mass is conserved. Do you agree? Right? Because from this instant to this instant, so this is my material. So because the material mass is conserved, right? There's no evaporation. So this material volume equals this material volume. This is T0 and this is the T. T multiplied by the VC equals T0 multiplied by V. So be very, very careful about this relationship because the mass is conserved. So I have this one, say, this is T0 minus T0 divided by TC, chip thickness, equals to R. So this is sin alpha, this is sin alpha. Alpha is rectangle. So this is US for serial, and US Fs multiplied by Vs equals this one. This is for serial, and in the shear direction. So this is UF divided by UT can be obtained using this equation, right? So this is UT equals UF plus US, friction and shear. And then we have all these is the equations, and then this is our first example. The example says that we have orthogonal carding being carried out T0 is an uncoloured chip signal. T0 is 0.1 millimeter. V is the cutting speed. So alpha rectangle equals 10. And the width of car, width called omega, equals 5 millimeter. We also found that TC, the chip thickness, equals 1225. And you should know that the chip thickness is usually higher than the uncolored chip thickness. Why? Because of friction, okay? The friction slow the speed of the chip. As a result, the chip is thickness of chip is bigger than uncolored chip thickness. IFC cutting force equals 500 Newton and thrust force equals 200 Newton. Now, what is asked? We need to calculate the total energy that is dissipated in friction, right? Friction energy as a two-chip interface. So how to calculate this one? So friction energy, the percentage, okay, percentage of the total energy that is dissipated in the friction. And so we know friction energy is the friction energy and divided by the total energy is the percentage. Is the total energy. And we already know that the friction energy equals the F. F is the friction force along this is the rib face, F. And multiplied by Vc, and Vc is the chip speed. Right? Force multiplied by this guy's speed equals the power. And the total energy is cutting speed. I'm cutting it. Right? Cutting it Fc multiplied by V. And this V is my cutting speed. I want you guys to draw down to do something. That's the reason I ask you to pull out a piece of paper, use some pencil or pen, and to do some simple calculation. So, and this is a V and a Vc. Right? So V, we know that because the mass is conserved. Mass is conserved. So that's the reason the T0 and uncolored chip thickness multiplied by your V, right? Your V equals your TC is the chip thickness multiplied by your VC. VC is the chip speed. You agree? Because as I said, there is no evaporation. The evaporation is ignored, right? So how much energy how much material removed in this direction, in all this it goes just above this is rib face. Right, Michael? Yeah. So that's the reason T0 multiplied by my V in this direction, current speed, must be equal to the two chip thickness multiplied by the chip speed. But definitely, we should have time t here, but because both sides contain the time t, just to cross out the time t. So we can have this. Okay, so VC divided by V equals TC and this T0. So T0 TC equals R. We call this a ratio, the chip thickness ratio. And it equals T0 is given, and T0 is 0.1, and TC is 0.25. We have this one already. So this gives us a 0.40. So this is R, this equals R. So we know here, this is VCV, we have F multiplied by R equals FC. Because this guy equals my R. Right? Right on? Okay. Based on this one, I also know that based on this diagram, I also know that the F, the friction force along the rib space here, this F equals my resultant force R multiplied by sin beta. So F equals R multiplied by sin beta. Right? Also, if I look at this right angle, I know that the FC, because I'm going to use FC here. FC equals the same R multiplied by cosine beta minus alpha. Yeah, this side. So I will have is FC equals R cosine beta minus alpha. So why I have calculated FC? Because I have this my F and this my FC. I need to use this diagram and the same R, but I decompose this guy orthogonally into two rectangles. One rectangle, this one is one, this one is one. Right? Ready on? Okay, and then we have, based on this one, FC is the cutting force. And I also just record this FC and FT. So these two guys, they are in the orthogonal, in the triangle, right triangle, right? So the R based on the Pythagorean theorem, R equals this FT, the stress force square, and plus FC cutting force square, and this is the square root. And you just plug in. FT is obtained, FC is obtained. So this equals 500 FT of 200, and that means 200 square per FC is 500. So this gives us 538 Newton. So this is my total R. Right? After I calculate my total R, I can calculate my F. And my F equals here. So FC, calculate FC. This. So after I get here, okay, I just put it in. So this equals 538 cosine and beta minus alpha. And alpha equals 10. Alpha equals 10. Alpha equals 10, that means beta minus 10 degree. So FC, I know, right? See, FC is a 500 Newton. So I know, no, this is a 500 Newton. So this is only one equation. See, this equation, I only have beta. I use another color. I only have beta here. So this one turns out to be the beta. I can calculate the beta. And beta equals the 31 and 47 the degree. So this, I calculate the beta. Right? After I calculate the beta, my R is known. Calculate beta, I can just plug in. So this one and tells me F equals R. R equals 538 Newton multiplied by sine beta. So this, I can calculate this F. And this F turns out to be 283 Newton. So this is my F. Because I'm going to use F and FC. FC I know 500. Now this here I'm using F. Right? And then I just plug in because R I know for the 4. So we just we denote this one as the first equation. So plug in into first equation, and we will have 5283 Newton multiplied by 0.40 and divided by FC. FC is 500. And so this gives us about 22, which equals 22%. You understand? Okay, this problem contains two things. First one, on how to calculate the percentage of the friction energy with about total energy. How to calculate total energy and how to calculate friction energy. And then we use the force diagram. My force diagram. This is R. This R can be decomposed into two red triangles. One is along the rig face and also perpendicular to the rig face. Another one is along the current direction and also the thrust direction. The same hypotenuse, a different red triangle. Question so far? No question? Just don't underestimate the importance of this. This is very, very important. If you don't understand this one, if I give you a problem, ask you to do it in 20 minutes, it's still be a challenge. If you understand it, everything is good. Okay? Understanding is most important because our midterm and final will be open book. But still, you need to understand. If you don't understand, you need to spend a big amount of time and to review everything and then work on it. Questions so far? No question? No question. Let me take a picture. I'm going to post this one on the canvas.
Does it take a selfie?
Huh? Say again?
So I thought you were gonna take a selfie.
No. I don't have that addiction. But now I'm old. I don't want to do anything anymore. You can see my through profile. I still use the photo I took 12 years ago.
Photo you used 12 years ago.
Yeah, it's very the young guy, right? With dark hair, but now it's the with hair.
Let's see. Yeah.
Okay. Okay, this happens to everybody, okay? 20 years ago, I don't know that, but now I realize that. Okay, our second problem is also about the energy, cutting energy. So we asked to compare the forming and the machining energy. So when we do something and we need to compare and how much energy will be required. And so here are the two problems. The problem is we have two cylinders, same material, a new 304 stainless steel, and each with a diameter of 10 millimeter. So 10 millimeter, the length is 150, and these two guys are to have their diameter reduced to 9. Okay? Understand? This is my original diameter, and 9 is my final diameter. So I want to do two things. First one is by pulling it in tension. By pulling it in tension. This is the extrusion. This is the joining. Right? Second one is machine. You just machine it, use the lathe to turn to cut it. So calculate the respective amount of work is involved and explain the reason for the difference in the energy dissipated. So it contains a lot of information. So remember, draw down. The initial diameter is 10, and the final diameter is 9. One is the drawing, another is the machining, turning. Okay, I'm on to for drawing. If you pull the load, okay, if you pull load, the W, the work or tension. Let me use the W in tension. So this is drawing. So this one equals the stream energy, the specific energy multiplied by volume. Right? The specific energy can be obtained from the table, and this volume, the volume change actually, the volume change. So this is U. How to calculate this U? So this U is calculated using this equation from 0 to epsilon 1 and sigma and d epsilon. And what do we call this one? The string energy density. Oh, right? This is called string energy density. This is called string energy density. That means this is the energy, if we want to do it, this is the specific energy, the energy per unit volume, and you need to do the work. Are you taking CE with all the semester? No, you have not taken. The CAE, computer aided engineering.
No.
Although this is, and this one will be introduced in CAE. So this is the string energy density, we call it Olympic. And the string energy density. Right? So this one, this is the true string. We have the true string, and you know the true string, right? So in our homework 3, I ask you what is the true string is, right? Get it? Okay, true string is denoted using the epsilon. So this is epsilon 1, so this is logarithmic, and d0 divided by d. So this is initial diameter, and this is the final diameter. So this one gives us log. So our initial diameter is 10. Our initial diameter is 10, and this final diameter is 9, right? Right. Okay. So if we just, I'm sorry, here is a step. So if we just put it here, calculate it this way, we have 105. So this is my epsilon 1. So I'm going to take the derivative. I'm sorry, and do the integration here. My lower upper limit is epsilon 1. And then from table 2-2.2, we can calculate this K and N. So for string energy, right? So this for the K, for this case, for this material, K equals 75 megapascal. So this is N equals 0.45. So this K and N is related to the string energy, the power of the string energy, the equation of the string energy. So this is U, right? If you just it's a U based on this one, the U equals K. So this is sigma here. This is sigma K epsilon 1 N plus 1. So this is N plus 1. So this you just plug in, and we have 1275 multiplied by, so this one we just got it, 105 N plus 1 1.545. So then here is 1.45. So this gives us 33.5 times 6 Newton meter per cubic meter. So Newton meter is the energy, cubic meter is the volume. And so this is the string energy. Any questions so far? Sigma and epsilon, there is equation. Is
that because it's sigma equals K times epsilon to
yes, I'm sorry. Sigma equals K epsilon N. I'm sorry. So this is a gap. Okay? This is a gap. Right, thank you. This is a good question. I forgot to write this equation. That's the reason. It's also computer. So this is my U, and this is the string energy density. And so this is U. After you get this one, and you can get based on this U, my W tension. My W tension equals U. 3 energy density and multiply the volume. What's the volume, guys? What's the volume? Volume change. I'm talking about volume change. The volume change. This equals pi E0 square over 4 minus pi E final square over 4. Is that right?
Many length.
Yeah, length, I'm sorry. Yeah. Length is 0.5. So this is 10, radius is 10, and that is 9 radius. Okay, pi r squared is pi r squared is the final one. So if I use pi d0 square 4 is the original cross-section area, right? So this is my final cross-section area. The difference is the change, right? Then multiply by the length. If this is correct.
Assume that the length doesn't change.
Length does not change. Yeah. We just prove it. Just prove it. So this pi equals volume. So this U 3, 3, 5, and or 6 multiplied by my volume pi. I have a quarter here. Is that correct? Pi d square is the total. Difference. Yeah. D0 square minus d square multiplied by 0.15. Right? So D0 square is a 10 millimeter. So remember, here the 10 millimeter equals what? Equals 0.01 meter. Right? So D equals 0.009 meter. Be very careful when you need to use the standard unit for length. Standard unit equals is meter. So here is also meter for the 5. Right? So here this one turns out to be 1580 Newton meter. So this is the energy you need to use. Questions so far? For drawing. However, and for the machining, so this is the A for drawing, for pulling, we say pulling. And B is turning. So for B is turning, how to calculate the turning? And you need to material removal, and what is the material what is the volume and of the material you just remove, multiply by the specific underlay for turning, okay? So this is the volume. So this is volume. This volume equals the same thing, I over 4, and this is E0 square minus E0 multiplied by is the length, right? The length of, for this case, and we use millimeter because the spring underlay I will be using millimeter. So here, we use millimeter here. So here is a 10, and here is a 9, so it's 150 millimeter. So this one gives us the 2240 millimeter square. So here is the volume. This is understandable, right? And then look at for this the same for this species material and nude 304 stainless steel. We can check. This is table. We check the table. And 8.3, the steel underlay. The specific underlay in machining. And for this stainless steel, we have for stainless steel, we just use the species for stainless steel is around 3.0 to 5.2 W to watts multiplied by S divided by cubic. This is a millimeter. Right? So this is a typical for stainless steel in machining of stainless steel. We check the table 8.3. So we will not use the minimum one, we will not use the maximum one, we just use the middle. We just use the middle one. The middle one we select 4.1. Right, 4.1, we just select 4.1. We select the mean value. Medium value also. So 3.0, 5.2, and we select 4.1 here. This is in the middle, right? Range. This is a range. I just select the middle one. We select 4.0, so this is a unit, and we can just calculate the work for turning equals the volume, this one 4.1 multiplied by volume. So this gives us 4.1 multiplied volume is 2240. And so this one is 9180 Newton meter. So this is in machining the work is almost 5 times higher than that for tension. The reason for the large difference between the two underlays are that the tension involves very little strain, and B, there is no friction for the tension. So this is how to calculate. This is the underlay. This is the sphere underlay density. This is specific underlay. Sorry. This is the specific underlay. This is a sphere underlay density. The same thing. Any questions so far? If I give you the similar problem in the middle, can you finish it, right? Good.
You said it's because there was no friction and tension and what's on?
So there's no friction for the pulling. You just pull it.
Then you said one other thing.
Another thing is the tension involves very little strain. Very little strain. Tension involves very little. Distribution is low. But for this is the carding, you just card it off, right? The large table machine. Any questions? And so the question I move on to the third one. Third is the Frank Ware. And how to calculate if we have this is if I give you some information, how to estimate this is how to estimate the time. So VTN, V is the velocity cutting speed, and T is the life of the tool. N is associated with this material cutting condition. C is constant. So we know that, and we also here, and this is a modified one. Okay, for our case, and we just use our original and Taylor theory. This is Taylor theory. Here is one example: a tool and material combination. A tool material for this combination, and we have N equals 0.5 and C equals 400. And how we asked to calculate the percentage increase in tool life when the cutting speed is reduced by 50%. We know that V T N equals C, right? And C is a constant. And for this is the tool for tool and the material combination. And C is a constant. And N equals 0.5. See, if I say if my cutting speed is decreased by 50%, and what is the percentage of my life T? And how to do that? Because this T, it states that V1, T1, right? Multiplied by N equals C, right? So this is for second case scenario will be VT, the second cutting speed, multiplied by corresponding tool life T2N. You agree? You agree, right? Because I say this is a constant for the same tool material combination. This is constant. So N, I know N is half. N is 0.5. N is 0.5. That means V1 T1 equals V2 T2. Right? And then we can get this is the square V1 square is this square on the left hand side multiplied T1 equals V2 square multiplied by T2. Right? Okay, so T2 is my second case scenario and T1 is my first one. So this equals the cross T1 here V1 square and this is V2 square. Right? Okay, so this one can be written as V1, V2, and square. You agree? Now I say if my V2 right, equals my 50% of V1, then my T2, then T2 over T1 equals V1 0.5 V1 and square. This gives me 4. Right? So that means the tool life for my second case is 4 times of your original tool life. You understand? So what is the increase? The increase means that a T2 minus T1 divided by original T1. And for based on here, I know T2 equals 4 times T1 minus another T1 and T1. So this gives me 3 T1. That means increase. The two length increased by 3%. Sorry. Three times higher. 4 times is as long as 4 times higher, but the net increase is 3 times. You understand? Questions? If I just make some manipulation and change this n, or just change the requirements, and you are supposed to be should be still be able to do the calculation. Okay, this just based on these two length equations. Okay, everyone. So this is pretty much what I have today, and I will have the